Welcome to the Cosmic Pie Podcast, episode 34, year number 3. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live from the campus of the University of North Dakota here in Grand Forks, North Dakota.
Yep.
We do have a live chat feature that's running, so if you have any comments or questions you'd like to ask us through the podcast, we'll do our very best to stop what we're talking about and maybe answer your questions.
And try to answer your questions. We do kind of vet, but it's just us. So, there's no producer sitting here going, oh, yeah, we'll let this question through.
And no guarantee we give them the right answer.
That's very true.
In fact, some answers are actually all dependent on your opinion.
Yep.
They're not necessarily hard, cold facts.
Right.
Because we don't know everything in science, even though we'd like to.
We don't, and science in general doesn't know everything. So
yeah, and if we did, all research would stop, and we just teach what we know, right?
Right.
The mass accumulation of knowledge.
And
in
what
fact,
a boring world that would be.
no, because we wouldn't do it actually now. We just get an AI device to do it.
True.
So we'd be sitting home at the beach,
I don't
drinking
think that would
pina
happen.
coladas from a glass with a straw hanging off of it.
Yeah, a little
In
umbrella.
90-degree weather all the time.
Little
But then we
umbrella.
wouldn't have any money because we wouldn't be able to work, you see?
Right.
So we couldn't
That's
afford to
what
do
I was
that.
getting at.
We'd be serving the drinks at this location.
That's probably more correct.
Now it's a good time to do the
The disclaimer,
disclaimer.
which, as we've said, it's just the two of us, folks. Anything we say is the opinions of myself or Wayne, not those of the University of North Dakota or any body related to it. So,
Right. And after we are done, usually the next day we upload the podcast as on Spotify. So if you'd rather go to Spotify and watch us later on, then you have that option. In fact, watch us live on YouTube and then go to Spotify the next day.
right, that's the best way.
Because you're going to miss things. We just say so much. Right? So you really need to play this podcast like several times
Yep.
in order to make sure you get everything, all the juicy nuggets that we say. Now, Robert,
Something like that.
what has been in the news lately? Lots of
Lots of stuff, especially about comets.
comets. It's been all
Yeah.
over the place. So maybe we should start there. What do you think?
Sounds like a plan. So here we go.
Okay, so the one comet that we hear a lot about, and we're going to talk about that here in a few minutes, but that's not it. So
No.
the one you hear a lot about is the one that some people suggested came from it's an alien spacecraft from
spacecraft.
some other star system, and they're
Yeah.
on a 5-year voyage to explore the unknown.
No. I think you're
Oh, that's
mistaken.
Star
That was Star
Trek.
Trek.
Oh, okay. 10-year voyage?
It's 5-year mission, but but at the same time, it's like, yeah,
This is not it.
it's an interstellar wanderer, but it's not a spaceship.
Yeah, this comet is not that comet, and it can get confusing. This is Comet Lemmon. So what it is actually a comet that you can actually see if you have a decent-sized pair of binoculars or if you're in a really dark location.
Right.
Now, the comet right now, as you see on this slide, it shows you the position at different times throughout this month, October. It's roughly near the area of Ursa Major, and that constellation, that part of the constellation, we call the
Big Dipper.
the Big Dipper. So if you can find the Big Dipper, then you hopefully can spot the comet. The problem is the Big Dipper, at least from our location, the northern hemisphere, this time of the year, after it gets dark, is really low to the horizon.
Right.
Which means this comet is below the horizon, essentially. And even if it, in a situation where it peaks above the horizon, you got to have a nice, number one, nice clear sight line to the comet.
So you got to have no trees or buildings in the way.
The other problem is you're looking through a lot of the haze of the atmosphere,
Right.
and it makes it much more difficult to see the comet itself. But if you wait long enough, I don't know, 5:30 in the morning, a.m., 5:30
Okay.
a.m., and you go out, then the comet is high enough in the sky that, at least from the location where I live in the southern end of Grand Forks, with a pair of binoculars, you can see the comet. I have seen it a couple different times.
And it should in the morning start getting higher and higher, correct?
Well, look at the location and where it's
Yeah,
going.
that's what I was looking at.
It gets brighter and brighter, but yeah,
it's going to get lower and lower.
Yeah.
Which means we missed our chance.
Well, no, there's a trade-off there of early morning, it's going to get brighter.
okay.
So you're still going to be dealing with the early evening. But don't forget the Big Dipper is circumpolar.
Right.
So you have to time it out right and see. It can go
Okay.
down, so then in the evening is the best time to observe it,
Right.
right?
And we're kind of hoping that is so we can show you some pictures we took
Right.
of it.
So the thing is the brightness. We want the brightness to increase dramatically. And right now, even in a large pair of binoculars in sort of the suburban part of the city and the suburbs, it's fairly faint.
Okay.
And it's definitely, you cannot see with your eye alone. You definitely need a telescope or binoculars to see it. In fact, even in a small pair of binoculars, I couldn't see it on most mornings I'd look until it got high enough in the sky to get
Yeah.
above that haze. With a really good pair of binoculars, like 20 by 80s that I have, and they're hard to hold, they're really heavy. So
yeah, I was about to say.
if you want to scan through the sky, the best thing to do is get a chair that lays flat and just lay on your back with the binoculars sort of perched on your face
Yeah.
to brace them, and then scan the sky, and you'll get tremendous views, of course. But they're really heavy, unless you have a tripod or something like that to hold them. But anyways, I could easily see it in those big binoculars. But
Okay.
they're still relatively faint, because the comet is not like a star where all the light comes from a single point, essentially.
Right.
And
it's spread out
It's
over.
spread out over large size, which means overall what we call the surface brightness is fairly low. And if you have a bright sky like you do in the cities,
You smear it out.
yeah, it washes it out, so it makes
Yeah.
it much more difficult to see. But the main thing about this comet is that some predictions now. What do we know about cometary predictions in terms of brightness? I hate to say it, but
They never work.
yeah, there's been many cases, in the past. Comet Halley was one,
Yeah.
and Comet Kohoutek, which is before my time, that was predicted to be extremely bright and disappointed a lot of people.
Comet Holmes, I remember I've mentioned it a few times, was supposed to get really bright and then broke up on them.
Yeah.
And just things like that happen.
That's sometimes you hear when the comet's first discovered, oh, it's going to get 5 times brighter than the full moon. I've seen that several times
Yeah.
too, which turns out to be wrong. And it wasn't even a right prediction. It was just a fake prediction to get you to click on the story.
Click on the story.
Yeah, so it's just misleading anyway.
And as we discussed in some of our earliest episodes, a lot of science news out there is just that. It's clickbait. It's made to make these things seem sensational.
But what determines the brightness of a comet, Robert? Do you want to address that a little bit, maybe?
How close it is to you, how close it is to the sun, and how well it's outgassing.
So that last point, then, is the fact that a comet doesn't shine light like a star.
Right.
What it does, it gets energized by mostly the ultraviolet photons coming from the sun, which are really energetic. And that causes the atoms and things, when you think of it, to be energized such that when they like to be in a lower energy state, their electrons, if you can think of that type of model, being in a high energy state because they've been boosted to that level by the interaction with ultraviolet photons, they drop down to the lower energy levels and then emit light in the process.
Right. Essentially, they're like fluorescents.
Yes.
They're taking high energy photons and turning them into low energy photons.
And then there's the reflection
And
process
then
too.
there's reflection.
Again, comets have dust, and dust will reflect light. Now,
Yeah.
that's invisible. If you actually have an infrared camera and looking at it, then you're actually going to see the dust emitting light of its own. We call that thermal radiation.
Yep.
Because the dust gets heated up, and if you heat dust, it loves to glow at infrared wavelengths.
Everything glows if it doesn't have an absolute zero temperature.
Exactly. Which means everything emits light,
Yeah.
including us.
Including us.
So, Robert, if I want to catch you ripping off the 7-Eleven and it's a Friday night and you're running off with the ATM machine home behind
okay.
you, should I be above looking down at you with my drone using an ultraviolet camera or an infrared camera?
Infrared or microwave?
Yeah, because given our internal body temperature, that determines what is the wavelengths that we are the brightest at. That is where we're emitting most of our light.
Yeah.
And it's mostly in the infrared part of the electromagnetic spectrum. So that's why you see, like, I don't know, in the military when they're at war, people are using infrared goggles to see the enemy because they show up very brightly, usually relative to the darker background at
And
night.
there's nothing you can do about it. Insulating yourself will work for a little while, but eventually your insulation heats up.
Yeah.
Welcome to thermodynamics, folks.
Yeah, and you can even pick out animals like deer and everything else,
Yep.
and dogs and anything like that running around at night in infrared because they do the same like us, emitting
Right.
those infrared photons. So yeah, dust particles will do that for the comet.
And Wonder Goon's asking, are you saying we sparkle? In a way, manner of speaking, yes.
Well, the more money you put in my hand, the more you sparkle. So that's a hint.
Oh, Lordy. All right. But you can see Comet Lemmon.
If you have the equipment, if you
Yeah.
have the technology. And here is a beautiful image taken of the comet. So if you have a really nice telescope, you can get things like this.
And so that blue-green is, as we've mentioned before talking about comets, is the cyanogens, the carbon-nitrogen molecules that when they're energized by ultraviolet photons, they glow a nice bluish green like that.
Wouldn't it be like cool? And this happened already not that long ago. This would have been somewhere around 96, the summer
Okay.
of 96, I believe it was, 1996. Comet Hacky Tacky.
Yeah, I remember it. Yeah.
And that went right overhead at night.
Yes.
And it was like this. And that was with the eye. You could see this.
Yes.
That big long tail stretching like, I don't know, it was like 90 degrees at least. Right?
I remember getting out of one of my numerical methods classes so we could walk to the observatory on campus and look at it through the telescopes. So,
And I remember being in Nova Scotia in a dark site while looking at this comet,
yep.
sitting in a field, empty field, looking up, and a comet almost stretching from horizon to horizon. It's just fantastic. And
When we get a good one, it's a good show.
that is the best comet I've ever seen.
Yeah.
And I was around to look at Comet Halley last time it passed through in
It
1986.
was a dud last time.
It was very low in the south, when I remember right, and it wasn't that bright. And it was
Right.
in the winter months. It was cold and miserable, and you're out there trying to get it.
Especially in Nova Scotia.
Trying to find it. Well, it doesn't get that cold. Actually, it gets a lot colder here.
Oh, okay.
It's on the ocean, on the coast, so it's
So it
moderated.
mitigates.
Yeah, the Gulf Stream moderates the temperature a bit. So
Right.
we always get the extreme temperatures here and range of them. But yeah, you can get sometimes some fantastic comets. And the thing about comets, in some sense, is the scary part about comets, is you never know when one comes,
Right.
for sure.
Because you never see it until it starts outgassing like this.
Yeah.
And starts glowing.
And that's sometimes can be very scary. You can get comets that come through maybe for the very first time because
Right.
they've had their orbits perturbed by the gravitational interaction of everything in our solar system, essentially. Or it could be like the next comet we'll talk about in a second, where it comes from another star system. So it's the
Right.
first time coming in. And the scary part, as I mentioned, is you don't know where it's going until you calculate its path or trajectory. So you could imagine an inbound comet, and it's like, uh-oh,
Yeah.
there's an intersection coming with the planet Earth in about 6 months. What are we going to do about it?
Right. And the answer is not much. Grab a lawn chair and a cooler of mojitos.
Go out with
You
a
know,
bang?
right, because we won't see it until it hits about orbit of Jupiter usually, where it outgasses, starts getting hot enough to outgas enough, and by then it's like 3 months away.
And we can't send Bruce. Well, he's in rough shape right now. We'll have to
Yeah.
send somebody else.
Send somebody else.
But yeah, unfortunately.
So,
But the
and
comet.
this is one of those that we got to worry about.
Well, this is the comet that has been making the news a lot since what, July or something like that? Yeah,
Something
July
like that.
1st. On Canada Day is when it was first spotted. Just a coincidence.
Yeah,
Now, this is the Comet 3I Atlas. This is the one where an individual has been making the rounds, and he's still making the rounds.
yep,
I was trying to say that there's a possibility that this comet is an alien spacecraft. In fact, I've written down words, if you like, of what he supposedly said during an interview, and he gave the odds. And I don't know if this is actually true, but he gave the odds, because I didn't listen to it directly, his words, 30 to 40% that it was an alien spacecraft.
oh, jeez. Wow. And this is why I see reports
Is
now
there a
where
chance,
people
30 to
are-
40% chance, like you're an idiot?
Yeah.
I'm
I
not
mean,
saying his name, so I'm not getting in trouble here.
You know, but at the same time, I've seen reports of this same individual that they're saying the university that he worked with for, or I don't know which it is, should sever ties with him and disavow the whole scenario because, sorry, folks, it's not an alien spacecraft. There is a 0% chance of that. Oh, well, okay. It's close enough to be practically zero. You know, in science, you figure out that there's never such thing as 0%.
Well, as Bon Jovi says, he gives science a bad name.
Yeah, and that's my problem with him and why I agree. You know, universities should be disavowed.
Oh, I just thought, I know what's going on. I know why this guy's, he's blinded by science.
Ah,
That's why
Yeah.
he's saying this, you see?
Yeah.
That's the reason.
but in the end, it is an interstellar object. It is coming from outside our solar system. That's something that none of us have ever disagreed with, really. But it's a comet, folks.
Yeah, and actually, every comet is different in its own way.
Right.
And it actually, like fingerprints, you could think of it that way, right? And this object has shown nothing but the fact that it has all the characteristics of a comet.
Right.
And there's absolutely zero evidence
That it's an alien spaceship.
that it's some alien spacecraft or something that your great uncle from Alpha Centauri is coming to visit you or whatever you could say. Now, the interesting thing about this comet is that it passes fairly close to Mars. In fact, the slide kind of shows you the different points. So it was discovered at position 1 on July 1st. That's in the top of the plot. Notice at position 2, it's really close to Mars. Really close, still, 30 million kilometers away.
Yeah.
But it gives an opportunity for spacecraft that are orbiting Mars or are sitting on its surface or roaming around that try to take an image of this comet. And the reason why that's interesting, because it wouldn't be otherwise, is because when this object passes Mars, the Earth is in a bad spot to observe the comet.
Yeah.
And because of that, spacecraft that are near Mars then have a much better view. If it wasn't for that, if the Earth had a great clear shot, I mean, we could use all of our telescopes on the ground to have a good shot of looking at it. But anyways, that's not the case. Now, after that, notice that it passes by the sun. This is when it gets to position 3 at its closest point, which would be on the end of this month, so on October the 30th. And that's a distance of still 210 million kilometers. And then it moves away from the sun. So it's outbound. So it's on a path that will take it out of the solar system. It'll never come back. It's on one of these hyperbolic orbits.
Right.
Which means it's traveling too fast to be in a bound orbit. And therefore, this is our one and only shot of making observations of this comet.
Right.
Unless, of course, in the future, we devise technology where we're able to
Go out and chase it down.
Some maybe like with robots or something, so you don't have to worry about carrying McDonald's food with you and oxygen.
I would like to point out that white curve, though, looks almost like a straight line. This thing is screaming.
Yeah.
This thing is moving really fast.
Which is not surprising given what is the relative speed of stars that we see around us
Right.
and in our galaxy.
It was one of the reasons we recognized it as being interstellar.
Yeah, so it's typical of this sort of thing. Anyway, so there are more observations that come.
I moved ahead a little too
Yeah,
quick.
so there are
Sorry.
more observations that come. For example, JUICE is going to observe the comet in early November, so where it gets by closer to Jupiter in that sense. And so we'll see where things go from there. As far as I know, there are no plans to chase it down with any spacecraft. Number one, we don't really have a spacecraft that can do it efficiently. Number two, you can try to redirect like the mission that's orbiting Jupiter right now that NASA has and get it to go out there. Some people say it could do it. Other ones said no. So I don't know.
I would be amazed if it had enough.
The latest I heard was we should have started it like a month or so ago.
Right.
And now it's too late anyways.
Right.
That
That's
is
what I'm saying. It needs a lot of propellant to get a lot of thrust going in a very short amount of time.
Yeah, Juno was the mission that they were going to
Yeah.
redirect because it's pretty well done.
Okay.
And so they were going to redirect it, and it would have had a chance to get fairly close to the comet. Not super close, but it's too late now. That decision wasn't made.
Right.
And you can't do it now. You know why?
Because it can't catch up?
Even if it could, they still can't do it today.
Okay.
You know what I mean?
Because everything's shut down.
The government shut down. That
Yeah.
includes most of NASA.
Right.
So even if you had made a decision just prior to the shutdown, probably you wouldn't have
been able
classified
to
that
do it.
as necessary personnel that need to keep
Right.
working, and the thing would be shut down, and you have to wait for the shutdown, the government shutdown to be over, and then it's too late, at
Yep.
this point. Because it's been going on for what, 2 weeks now or
2
something?
weeks, something like that.
Yeah, so anyways, so much for that. But that doesn't stop other people from getting images of it. So here's an image of the comet, and the arrow's pointing to it. That arrow's not in space, I put that there. Just because some people, you never know, right?
Right.
This is taken by the European Space Agency Trace Gas Orbiter on October the 3rd. And at that point in time, the comet was a distance of about 19 million miles away from Mars. So this is an actual spacecraft that it's orbit around Mars. So it knows where the comet's going to be in terms
Right.
of location. So just turn its camera towards that location at the right time and took this image. Now this image is tracking the comet. It's not tracking stars.
And so that's why you see those bright stripes.
Yeah, those long lines that you see there, short lines. And there's one in the far left, and there's a couple of them there in the upper right, and a few other ones. They're all over the place, actually, if you look carefully. Those are just star trails caused by the fact you're not tracking the motion of the stars themselves. You're tracking, in this case, the comet and doing a longer exposure.
Yep.
So because they're not moving at the same rate of speed, then you're going to get trailing in your image from the stars.
Yep.
Okay, so there's nothing mysterious about that. We can easily do that here on Earth because the Earth rotates. We're attached to the Earth. So you can just take any camera you can think of and take a long enough exposure of what you'd see in the night sky, and you'll see trails on all of the stars.
Yep.
Because of that motion.
In fact, I've got several pictures where I was trying to image an asteroid, and I kept the stars steady, but you can see the trail of the asteroid. Or in another case, I was taking a shot of a comet, and like this one, you can see the stars leaving trails, but the comet is steady.
And the really good one now, classic one you would say, is taking images of anything in the night sky and tracking the motion of stars. You can see all the satellites,
Yep.
the Starlinks, going everywhere. Right?
And there's streaks across the whole sky.
Yeah.
Now, thing I like pointing out about this image, and I'm just trying to move the cursor when y'all can't see it, is that you can see the coma.
Yes.
You can see the envelope of gas around that bright nucleus.
Right.
You have to look carefully because it does just look like more gray fog around that bright center, but you can see the coma.
Yeah, you can see the fuzziness around the brighter part of the comet itself.
You can even see that it's extended in one direction over the
That's
other.
right. It's extended towards the right
Yep.
rather than towards the left. And the other thing you notice here, too, is it's not a great picture of the comet, is it?
No, it's not.
I mean, the camera on board this spacecraft was not designed to take cometary
Pictures.
pictures or
So
images.
So you really can't see the tails. You really can't see any of these other things.
Now, so what kind of information does that really give you, this image?
Hey, it's there.
Public outreach,
Yeah,
PR
yeah.
type stuff, but it really doesn't give you anything
There's no
scientific.
scientific information here. Yeah.
No, you need something else like spectroscopy of it. Now, if they have more data, the European Space Agency, because they're going to look at it with other instruments as well, they haven't released it at this point in time. So they're probably analyzing it and maybe even coming up with a publication for it. So we'll have to wait for that. Now, the reason why I said a lot about these trails, here's a nice trail in this image. Now, this was reported as Comet. And it was taken by the Perseverance rover on the surface of Mars. So you stop looking down and you look up for a change, right?
Right.
And they knew exactly where the comet would be, and they took an image of it, and this is the image of the comet itself. And everybody was looking at it and say, wow, it's a cylinder in space. It must be a alien spacecraft. That other buddy is correct, you see?
Yeah.
But this is exactly what we get when we take a long exposure. As we demonstrated in the prior slide, you're going to get these type of trailing if you don't accurately track the motion of the quote-unquote comet in this case. And to give credit, the person that is shoving this idea of alien spacecraft, he even said, well, wait a minute, these are long integrations, and every camera you need to do an integration in order to see an object.
Yep.
Whether it's 100th of a second or it's 10 minutes.
Or 10 minutes or several hours.
So in this case, the exposure time was long enough that the object has this track, so it looks like a cylinder, part of a line segment in space. Now, NASA's closed, so they can't say anything about what results they've had received from the Perseverance rover in its
Yeah.
attempt to observe this comet. They'll have to wait till the government shutdown is over, unfortunately. So we
Right.
waited this long till October to do these images, and then we got to wait even longer unexpectedly. Now,
Yeah.
but since this has come out and hit the internet, everybody's oohing and ahhing, it was discovered that this is not even the comet. This is actually one of the moons of Mars, Phobos. It's a,
Let's say Phobos was the small one, isn't it?
yeah, there's Deimos and Phobos.
Yeah.
I think Deimos is the smallest one.
Okay.
Phobos is the larger one. And in this case, it's an old data set. It's not
Not even the new one.
no. And you can tell that. And how do you tell that? Well, go back to the previous slide,
Okay.
Robert, and we'll look for that.
That one.
So this is the one taken by the European spacecraft. Let's assume that the optics on this spacecraft is roughly comparable to what the Perseverance has on board the rover.
Which
right?
is not a bad
Yeah.
assumption.
Okay. Now notice the long exposure that's required to capture the image of the comet. You see a lot of these star trails. And notice a lot of them are very faint, but they're in the exact same alignment as the brighter ones.
Right.
Okay, so you're seeing a lot of stuff just at the faintness of the visibility of the camera, of the image that was taken here. Now,
Right.
Okay. Now, so in other words, the comet is not super bright. If it was super bright from this camera, it would have a lot shorter exposure time, and you wouldn't see any of those fainter stars. In fact, even some of the ones you can clearly see here, you would barely be able to see
Barely
them.
be able to see.
So if you go back now to the other image, notice in that image, you don't see any star trails anywhere. All you see is that bright little line segment near the middle.
Right.
So the exposure time was relatively short
Sure.
because the moon is relatively bright,
Right.
right? So if it was the comet, it should have been a lot fainter than what you see here, and you'd see star trails in the field of view of the image that's
Right.
taken here.
I'll buy that for $1.
And you don't see any of that.
Yeah.
So people should this is how people realize that, wait a minute, this is too bright to be the comet,
Right.
right? This is something else. And then people put two and
Two and two
two
together.
together and
They
discovered
went back and looked at the ephemeris of Deimos
and looked at the
Phobos and-
archives of images that were released and realized,
Yeah.
no, this is just an old movie clip taken of Phobos, right?
Right.
So yeah, so much for that. And NASA hasn't said a word, yes, nay, or yay, because they're not allowed.
Right,
Right.
because they're closed down.
Yeah. So anyways, what can you do about that?
Yep.
Okay. Now sticking with Mars.
Sticking with Mars.
You know, there's been well over 1,000 Martian quote-unquote tornadoes, what we
Yep.
like to call dust devils,
Right.
that have
Now-
been observed on the surface of Mars.
Yep. Now, what's the difference between a tornado and a dust devil?
Well, you tell me, Robert.
Okay. A tornado basically starts in the clouds and drops to the ground. A dust devil starts on the ground and goes upward. So these are technically dust devils because Mars doesn't have a dense enough atmosphere really to get a dynamic enough weather system for a tornado.
So I understand the dust part. Where's the devil part come up? Since it starts from the ground up, the devil's in the ground?
I don't know. I am not sure on that one, but you know.
You know, the only time that I've seen dust devils before, right here on Earth, and the best one I've ever seen, it was actually a weird situation. I was coming back from an observing run in Arizona, so I was actually at the airport in the middle of the afternoon in Tucson,
Okay.
and I looked over. I was waiting at my gate for my flight, and I looked over, and there was several people gathered around one of the windows looking out over the runway. And I'm thinking, okay, just looking at planes coming in or something taking off, you know. And here it's got like the military jets are right at the airport, right?
Right.
So they're always taking off and screaming and by and stuff, and hear the noise, and people are always looking at them and so on. And they were looking and pointing, and I'm like, you know, I don't. So I got up because I had lots of time waiting, right? Killed time, looked over, and here was the classic bent stovepipe of a dust devil.
Nice.
And it was beautiful and an extremely well-defined stovepipe because of the dust, right? Being in Arizona and stuff right out on the runway. And it was right out in the runway. And it lasted for several minutes before it dissipated. It was beautiful.
Yeah.
Like, it was unreal, right? I wish I would have had an image of it at the time. But this was before we were carrying cell phones around. And,
Oh yeah.
yeah, so I didn't get an image of it. So this was couple
But,
decades ago.
yeah,
but it was beautiful.
It's all convection currents. It's
Yeah.
all low pressure centers or high pressure centers, so the air is coming in or pushing out, and it gets a circulation going. And
Yeah,
you know,
I mean, I've
it's-
seen them in the distance in the fields and stuff. I've seen them like when I was down in Chile on observing run. They have a lot up in the desert and stuff. But they didn't have this classic stovepipe shape, constrained shape to it. That's what made it so spectacular.
yeah,
looking.
I one of the most spectacular I saw was on a playground one time when I was a kid, and it was just barely moving, but the leaves got caught up in the updraft, and so it went up 10, 20 feet that you could see it, but it was just this slow rotation in the air. We went and played in it.
Yeah.
Got our teachers upset because, of course, they had heard all the myths about the devil living in them. and things
I didn't
like
hear that part.
Yeah. There are legends that supposedly it's the devil trying to get out of hell and things like
Well,
that.
somebody who listens to our podcast on a regular basis, he once told me about a dust devil that he saw as a younger person, and he walked right up to it and threw his school books into it
Trying
just-
to burn them up.
just to see what it would do, right? Just an experiment, right?
Right.
So and it's a physicist, right? The person
That's it.
who did this. So
Yeah.
experimentation.
That's the key of science.
Yeah. So it's been several decades now that we've had the ability to image dust devils on the surface of Mars. So you can put a lot of this information together to try to track different features, like what are the winds actually like at the surface of Mars and so on.
Right.
Very important stuff. Very important, because if we're going to go to Mars, that is, humans are going to land there, we have to build the right structure and be prepared for these kind of things.
Right.
Now, if you want to go to the next slide, here's an example of what we're talking about. So this is an image taken again with the ESA's Trace Gas Orbiter. That's an
Okay.
orbit around Mars, the same one that used to take an image of Comet 3I Atlas. And this is an image taken of 3 dust devils back on November 8th of 2021. So it's the same kind of thing. You can see the shadow cast by these dust devils.
Mm-hmm.
And it's an open desert, dusty environment, so it's a perfect place
To
for
capture
the-
these.
for
Yeah.
these to occur. And you get the heating effects, the thermals during the daytime when the sun is shining. And yeah, so it's very interesting from that point of view. And if you go to the next slide, this is the interesting fact of what we have when you think about Mars, is the fact that Mars's atmosphere is so thin.
Yeah.
And because it's thin, and how thin is it? Well, it's about 1/100th that of Earth.
Right. I mean, your vacuum cleaner, the heart of your vacuum cleaner, has a denser atmosphere than Mars.
So you could just walk right through this thing.
Oh, yeah.
See, and not even worried about. That's the one thing, now you just brought up something I thought about. Remember the movie Martian?
Yes.
And they showed that huge dust storm.
Shaking the hab and
Yeah,
everything.
and it was
Yeah.
going to tip
No,
over the
wouldn't.
rock, and they had to hurry up and launch. They couldn't wait
Would-
for Mark Walney, whatever his name was,
Yeah, Mark Watney. Yeah.
Watney to get on board, right? And it blew. Wasn't it a line broke or something, and sent the thing through his chest,
Yeah.
and all this kind of
And
stuff.
none of that would happen.
None of that can happen.
Mars's atmosphere is just too thin.
Yeah, exactly. So
It's doing everything it can to lift dust.
yeah.
So, yeah.
And you can think of dust, you think of lint in the air, and all you got to do is make a little blowing motion. You can easily disturb the lint floating in air. So it doesn't take a lot then to levitate the dust.
Right.
And that's what you're seeing here. So anyways, it's no danger. It's not like when we're on Mars in the future that somebody's bent over tightening up a lug nut, and here comes a dust devil from behind, that's
Right.
going to flatten him and tear his right arm off or something like that, right?
Right.
So you don't have to worry. Don't have to worry about that kind of stuff.
It's not like Venus's atmosphere where a 2-mile-an-hour wind will knock you down because it's so much denser than here on Earth.
Yeah.
This is the exact opposite. Would take 100-mile-an-hour wind for you to even notice it.
Yeah, I mean, you'd notice it by seeing the dust being
Caught up.
caught
Right.
up into it around you, type of thing, right? So it'd be hard to really. So don't have to worry about structures have to be built to extend to be able to take an EF5 tornado equivalent here on Earth
Right.
or anything like that.
Right.
And therefore, we better build everything underground.
Well, might be there are other reasons for building
To
it
go
underground.
underground. It's not from dust devils.
It's not from dust devils.
So what are those other reasons since you brought it up?
Yeah. What are those other reasons? Radiation, solar wind, which I guess could be considered radiation, and meteorite impacts.
Yeah, so that's one thing about going into space is you have to worry about the activity of the sun.
Right.
Even the Apollo astronauts had to worry about that on the 3-day roughly journey to go from Earth to the moon, that they would be exposed to all of that hard radiation coming from the sun if the sun had a large like solar flare event.
And people worried about the Van Allen belts, which are belts of of high energy particles
Yeah.
around the Earth. And the thing to remember about radiation and the damage it causes is kind of like poisons. It's exposure density and exposure length.
Right.
And the thing is with the radiation belts, they blew through them so fast that whoop-de-doo.
Yeah, and they had dosimeters on them.
Right.
Personal dosimeters, which just monitor your radiation exposure. And we know that that radiation exposure is very minor going through the Van Allen radiation belt. You know,
Right.
some people say we never went to the moon because we can't get through the radiation belts.
Right. That's why I brought it up.
It's no, because we go fast enough. It's not like you're just strolling along
Right.
or crawling speed through them. You're zipping through them, right?
Right.
In fact, you have a lot of velocity at that point because you're near the Earth. You just got that boost from the third stage of the Saturn V. And over time, you slow down because Earth is pulling you.
Right.
So you're slowing down until you reach that point really close to the moon where the moon's gravity is stronger than the Earth's gravity. Then you speed up again.
Right.
And you can actually see that because there are lots of websites out there that actually will display like the old Apollo missions. So you can actually watch from start to finish like all of Apollo 11.
Oh,
or
wow,
all
cool.
of Apollo 13.
I haven't seen one of those
all,
sites.
I will send you the links. All of
Oh, yeah.
Apollo 17. And over that time period, they give you information about what is the current, distance of the spacecraft from the Earth, what's the current velocity, and all this stuff. And you can track it as it slows down, slows down, slows down. And then when they reach that point closer to the moon, where the moon's gravity dominates, then it starts speeding up again as the moon's pull is hauling the spacecraft towards it.
Cool.
So it's accelerating. So you get all of this thing, and you're still weightless. People, why are you weightless? Because the spacecraft, everything in it, including the people, are moving at the same rate.
Right.
So you don't push up against the wall or anything like that, unless you fire a thruster or something. That's about
And
it.
then you do.
Yeah.
And people are like, oh, there's no gravity in space. Of course there's gravity in space. It's just that you're free falling.
Yeah.
It's like being in an elevator where the cables were cut.
Yeah, exactly. You're falling down, and you're weightless at that moment if you neglect air friction.
Right.
If you had an apple in your pocket and you held it out in front of you and let go, it would fall. It would stay right there. It would fall at the same rate as you
Right.
go down the elevator. So you could be able to do all these wonderful experiments, and gravity's still there because when you get to the end, you really realize it.
You really realize.
At least for a split second.
Right.
It's that kind of a thing, right? So this slide actually shows you the location of some of these dust devils over the last several decades taken by various spacecraft. We have both the Mars Express spacecraft, that's the line of images on the very top you see there, taken with its instrument. And in the bottom of that, we have once again the Trace Gas Orbiter with its experiments. And then the map on the very bottom is the different locations where they have been spotted, these dust devils. So it gives you an idea that if you're in the polar regions, which is at the very top and the very bottom, you're not going to get a lot of dust devils because of the nature of the environment. Right?
That makes sense. It's not a lot of heat.
Yeah.
There.
In fact, that affected NASA because NASA has sent a spacecraft that was fairly near one of the poles,
Phoenix.
and it received a lot of dust on its solar panel,
Right.
and that they were hopefully that a dust devil eventually would come along
And
clean it off, and then they would get their energy back again to power spacecraft, and it never happened.
Didn't happen.
Because it was in a location where the probability of that occurring was fairly low.
Right.
So that's the trade-off there. Dust is flying around everywhere on Mars, so you accumulate dust on these solar panels over time, and that reduces the amount of light,
It's
and therefore electricity
and
goes
it's
down.
because of these dust devils.
Yeah, or dust storms.
Yeah.
So we do have, that took out one of the rovers too on Mars.
Yep.
We had a huge dust storm, and that was the end of it. So that's why you like to send up something that doesn't rely on solar panels, like, radioisotope thermoelectric generators, so
Right.
nuclear power, right?
Make 'em nuclear.
The decay of plutonium and use that heat to generate electricity and so on. That's the idea, anyways. So it's really cool. And just to kind of illustrate the point of what is the wind speed, because that's ultimately a major part of this paper. You can see, here's another example, if we go to the
Okay.
next slide, where we see a dust devil, and there's like an insert there on the bottom right showing you what it looked like at much higher resolution. And they're clocking wind speeds on the order of 38 meters per second.
That's fast.
And that, I converted that, that's about 80 miles per hour.
Yeah.
So very high speed, and that's on the surface, right?
But it's 0.1 Pascal.
Yes, that's
For-
the
for-
thing.
For reference, Earth's atmosphere is what, 107?
Yeah, Earth's atmosphere is about 101.78 something or something like that.
So
over 100,000 pascals.
yeah.
So yeah, the pressure varies a lot. That's way less than 100th the pressure of the Earth, but
Right.
that's an average number. The pressure, there's high pressure areas and low pressure areas like we
Right.
have on Earth, but you have extreme sort of events happening here on Mars in terms of the pressure changes. So at the time when this observation was done, 0.1 pascals. So that's just
So you wouldn't even know it was there except for the dust devil.
Yeah, and if you want to know the ratio compared to the Earth, just take 0.1 divided by 100,000. That's approximately what you get as the
Yeah.
percent of the pressure on Earth. So it's a very, very small number, way less than 1%. So
Yeah.
very interesting stuff.
So yeah.
Yeah. So the next thing that's in the news is a very beautiful image, and you'll see it in a second, of the jet coming from the galaxy M87. Now, M87 is famous in some sense, even more so now, because the Event Horizon Telescope, which is the system of radio telescopes spread around different parts on the Earth, and they use it as an interferometer. What that means is they look at the same target, and they each have their own like atomic clock, so they can time stamp the arrival of the signatures of the photons that are arriving. And then they take all that information from all the different independent radio telescopes and then correlate it together so they can say, okay, what did you observe in this little tiny window of time interval? And what did you observe in the next time interval, and so on. And you can put that all together in such a way that in terms of resolution, the system, the interferometer, acts like one giant radio telescope about as large as the extent of the radio telescopes themselves.
Right.
So if you have them spread around the surface of the Earth and it's all pointed in one direction, effectively, in terms of resolution, you have a telescope that's the diameter of the Earth.
In terms of resolution.
The other thing that's important here is what we call the light gathering ability, and that's the surface area of the collecting device, like a mirror or a lens, if you think of a refracting telescope.
Yeah.
Of course, if you have separate dishes, 7, 8, 9, 10 of them spread around, that collecting area is not the size of the Earth. It's the surface area of each of the dishes added together.
Right.
But in terms of resolution, it does work that way, which gives you very, very high resolution. In fact, because of that high resolution, we were able to observe a couple of years ago, I believe it was in 2018, if I'm not mistaken, the shadow of a black hole for the very first time.
And it was M87.
And it was M87. Now, we knew there was a jet coming from M87 from the center of it, and we speculated that that jet is related to the fact that it has a supermassive black hole at its center, and there's an accretion disk, which means material orbiting outside of the event horizon. That material is going to have lots of magnetic field associated with it, charged particles, so it's a really energetic, hostile environment. And they're not 100% sure how you create these jets. And I'll show you the image of the jet in a second. We don't want to do it yet, because I don't want to spoil this part of it. But it's still a work in progress. But we know it's related to wound up magnetic fields so that the jet gets collimated.
And conservation of angular momentum.
All of that, all the physics that you have to put into it. But it's a lot of, E&M, charged particles, magnetic field environment. So there's a lot of nasty physics in some sense to get right.
Yeah. Yes.
You can't just gloss over this and say, whatever, right? but there's
we
a
can
lot
make
of
this
important things.
assumption. No, you can't.
If you're a physics student or know anything about physics at the graduate level, if you think of the textbook that was written by Jackson, this is Jackson 100% that you need to, if you dissect the observations, to understand what you're actually looking at. Now, this particular galaxy is about 53.5 million light years away, which puts it not in our backyard. It's beyond our backyard, but it's certainly not on the other side of the observable universe or something like that. And by the way, the black hole that we've seen, the shadow of it, has a mass of about 2.4 billion times the mass of our sun. Now, to put that in perspective, our galaxy, the Milky Way, also has a black hole at its center of about 4 million times the mass of the sun. So clearly the one in M87 is much, much more massive.
But M87, if I remember correctly, is an irregular galaxy, and
It's elliptical.
oh, it is an elliptical.
Yeah,
Well, then
giant
there.
elliptical.
Yeah, right there. Ellipticals tend to be more massive. So
In fact, we know that almost every normal galaxy, is probably the answer is all normal galaxies, have these supermassive black holes sitting at their centers.
yeah, which makes me wonder: have they found any evidence of such in the heart of like the Magellanic Clouds?
No, not at the center.
Okay,
We're talking, they're probably too low of a mass.
right, and that's why I was asking.
Yeah, so they
so
have
there is a cutoff
yeah.
mass.
They're the most massive of the dwarf galaxies that are in
Right.
orbit around the Milky Way, the largest small Magellanic Clouds, but they are certainly not
They're not in the realm of the big
massive
boys.
galaxies if you compare them like to the Milky Way or
Right.
M87 in this case. And the thing to note there, but there are black holes in the galaxy.
Right,
I mean, we know that the supernova 1987A
which we had talked
probably-
about on the show. Yeah,
probably produced a black hole or a neutron star, be either one.
Yeah.
And we haven't seen any signs of it that's a neutron star. It might be a neutron star,
yeah.
but there will be other stars in that galaxy that have went supernova already before 1987A that would have been more massive and it would definitely have formed a black hole. So there are other black holes, but
There's not a supermassive.
at the center,
Yeah,
Now, and the other thing about this, these observations of the Event Horizon Telescope were extremely important at the time in 2018, because prior to that time, you could argue black holes don't exist.
right.
So a lot of these sort of paradox situations that you find yourself in, like how do I describe a black hole? And people argue if I take an encyclopedia, throw it into a black hole, is that information lost forever? Or does somehow that information come out even though you can't really read it in terms of bits and involved in the Hawking radiation? So
Right.
there's all these exotic type of stuff that we can talk about in a future podcast. So black holes have kind of been a talking point for many decades now, and very, very fascinating.
And we still have no clue about a lot of the facets and factors.
Yeah, it turns out that the environment and the really heart of these things are such that we don't have a good understanding from the point of view of gravity and what happens in these very small locations
Right.
to really understand.
If we can figure out a theory of quantum gravity, we may be
Yeah.
where we can start describing these
That's what we need. And if you think of movies, we mentioned The Martian, now we can mention Interstellar.
Yeah,
That was a great movie from that point of view, right?
Right.
And on there, they're looking for quantum information.
right.
That'll help them solve gravity. Remember, that was the whole kind of
I
a
do.
motivating theme throughout the whole movie itself. And that's kind of, if you,
I remember thinking much like the movie Stargate, where he mentions, figuring out the hieroglyphs. Oh, once you figure out the vowels, it all falls into place. And that was amusing to Egyptologists because that is the problem. Old writing systems did not include the vowels. So it was an inside joke on
there's
ancient
none,
languages.
there's none defined. 'Cause
Yeah,
they're-
right. So
Yeah.
there's all these nice inside jokes in a lot of these movies if you're familiar with the
Now-
material.
Now, for this object, if you make the assumption, which you could easily do, of course, that there are no black holes, for some reason nature doesn't ultimately make them,
Right.
something that stops them from forming, then you get around all these paradoxes. You only focus on the thing, what stops these from forming. You only have to work on that rather
Right.
than worrying about all this other stuff. But with these observations in 2018, if you weren't convinced already, now you are, because we took direct images of them, right?
Well, and I would argue that you're still dealing with We know how fast stars are going around these regions of space, so we know what mass is there, and we also know the volume because it's outlined by the orbits of these stars. And the only thing that can be that massive in that small a volume of space is a black hole.
Well, people argue that it's a high concentration of a huge cluster of neutron stars that's in that small volume of space, so you can't see it. That was some of the arguments that people had made in the past, especially in the 1980s.
Right. Let me see that work. I want to see the math of that orbital mechanics work.
Yeah. But not to keep you in suspense any longer, let's actually show the image of the jet. This is an image taken with the James Webb Space Telescope, so it is an infrared image. The center of the galaxy is sort of on the left side. That's the bright spot. And you can see the jet sort of going out towards the upper right a little bit there. And it's clear what it looks like. You can see the pinkish colors in it. They use for color coding the images here.
Yeah.
I mean, you can actually see a lot of structure in that jet itself, which is amazing. And actually, we'll show you some more of that in a second. But for length scale, you can see the bar below the galaxy, the center of the galaxy, 1,000 light years. So the jet, goes out at least 5,000 to 6,000 light years.
Right.
And it gets fainter as it goes out. So it's hard to see where the cutoff is in that sense. So very beautiful type of object.
And you would not want to be anywhere in this cone, even 2,000-3,000 light years away.
In fact, this jet is bright enough you can actually see it in a small amateur telescope.
Yes.
Which is kind of cool. So when people looked at it for the first time, they're like, okay, what is this thing sticking out from the center?
Right.
That would immediately capture your attention and then lead you down this road to try to figure out what this is.
What could energize with matter enough to blow out that far and stay cohesive.
Yeah. So if we go to the next slide, you actually can see the Event Horizon telescope image of the supermassive black hole at the center of this galaxy. That's on the right. And
so I'm going to say, so what we're actually seeing here is actually the accretion disk around it, and then that dark center is its shadow, across that,
exactly.
that
Yeah.
accretion disk.
And the other thing to note is there is differences in the brightness. The bottom part of the ring, as this orientation, is brighter than the top.
Right.
And that has to do with the rotation of the material in the accretion disk. And it's all relativity in this sense.
Right.
Right.
Because it'd be going fast enough at that distance. Yeah.
And the other thing is that you get the complete ring, and you shouldn't see that because the space around the black hole itself is warped to the point that light coming from material on the other side of the black hole relative to us, that light passes through that highly curved space, and you can see it. It's like taking a lens or something and bending it,
Yeah.
and then allowing you, like a periscope, allowing you to see around corners, essentially, right? And that's what you're seeing here. And you can trace out, where the rays of light would go, given the mass of the black hole, from different points around the black hole itself. And actually, it matches what you see here in terms of the observation. So
Right.
there's nothing mysterious about this observation. It's exactly what we expect in this type of environment where space is so highly curved. Remember, when we're talking about a black hole, one way to think about it is space is curved in on itself. So we always hear that light can't escape from a black hole. You'd have to be traveling faster than the speed of light to get out, that the escape velocity when you're closer to a certain distance from the center of the black hole is greater than the speed of light. But that's not the right way to think about it.
Right.
A better way to think about it is when you get to the point called the event horizon, where you can't see anything inside of the black hole. It's where space curves in on itself. So if you're inside of that volume of space, there is no way to get out.
There is no out.
There is no out. And then the analogy I think we used probably in the last podcast or one before is you can imagine you have a paper bag and you're at a lunch or a picnic and you're laying out, and it's a beautiful summer day, you're laying out on the grass with a blanket, you eat your sandwich, and then the bag is off to the side, and then you have a short nap, then you get up and say, okay, I got to get back to work. Then you grab the paper bag because a good citizen, you want to put it in the garbage can, and you close off the top of the opening of the paper bag and then walk it till you get to the garbage can. In the meantime, unbeknownst to you, an ant had crawled inside of the paper bag while you were sleeping because it sensed the crumbs left over from your sandwich. But as soon as you tie off the end of that paper bag, the ant is trapped inside of that paper bag. If it tries to crawl in one direction, it'll eventually come back to its starting point.
Right.
So any direction it crawls in, it'll always come back to the starting point. it's forever trapped inside of that volume of space.
Right.
That's how you can think of light being trapped inside of a black hole when you're within the event horizon of the system itself.
Yep.
And on the left there, we see detailed, the image taken with the James Webb Space Telescope. Well, these are HST images, some of them, and James Webb Space Telescope images. So the HST images are in the little insert that you see there. And the James Webb are the larger images that you see, looking at the details in the infrared. So you can look at the actual wavelengths. So you go at the top, it's image taken at 0.9 microns, right? So,
Yep.
so 1 micron is 1,000 nanometers.
Right.
So light, in terms of what we can see, goes from 400 nanometers to 700 nanometers. So this is 900 nanometers. So it is still in the infrared. It's not in the red. So we would not be able to see this with our eyes. As we go to the next panel below that, it's like 1.5 microns further in the infrared. Then you can see the numbers there, 2.77 microns, and then finally the bottom one, the 3.36 microns. So these are all infrared images.
And we're all getting cooler as we go down.
Well, it depends on the temperature of the material itself.
Okay, true,
So you have
because
to-
it would be dependent on the
Where the peak
brightness
is,
as well.
yeah. So
Good
in this
point.
case, that's the case. So anyways, so it's images like this, and you can take it once and then take images again and again, so you get information about dynamics, how things change with time.
Yep.
So you can monitor this kind of stuff, which is really interesting when you talk about it. So it's really, really cool in that sense. So and related to black holes is the observations now, and I'll explain these in a second, of a binary black hole in the quasar OJ 287. So orange juice 287.
Yeah, I was thinking the same thing when I saw the name.
Now, these images are actually very high resolution. In fact, they surpass the Event Horizon Telescope.
Oh, wow.
The resolution of this instrument, which consists of a radio telescope essentially that's in space,
Okay.
right, and instruments on the ground, in this case, several radio telescopes spread over the whole surface of the Earth on one side facing the target. That's known as VLBI, Very
Okay.
Long Baseline Interferometry. And it's a combination with this Radio Astron satellite, which was mainly a Russian
Okay.
vehicle. So these observations were done several years ago. Okay, so not done now. There's a lot of political stuff with Ukraine and things. So
Right.
all communication scientifically with Russia has been cut off since that war began. So this was done before that to gather these observations. But because this spacecraft is far away from the Earth at the time, about halfway between here and the moon,
Oh,
that
wow.
gives you a long baseline.
Yeah.
And the longer the baseline, the more resolution you can get, right?
Right.
Higher resolution. So the resolution of this instrument is 12 micro arc seconds.
Wow.
For the Event Horizon Telescope that took the image of the black hole in M87, it's 19 micro arc seconds.
Which is, for radio, is just, holy cow.
It
That's
is. It is extreme.
extreme.
And you want to know 12 micro arc seconds. That angle that you can resolve, just barely resolve, that is the angle that a US dime would display if it was 3.09 million miles away. I did the calculation myself.
Okay. Wow.
Or 4.97 million kilometers if you like the metric system better.
Yeah.
So a US dime at over 3 million miles away, the apparent size of that dime, that little tiny, tiny speck, would be 12 micro arc seconds. That's the resolution of this instrument.
Yeah. Now, again, this isn't going to show up the bank robber in any better resolution. It is radio waves. So,
Right.
yeah.
And you can see in the top image, the bottom bright streak, that is one of the vicinity of one of the black holes. The streak directly above it is the vicinity of the second black hole. So these are
Wow.
binary, two black holes in this system. And then the brightest one, which is above that, is actually the jet itself coming out.
Okay, so the jet is almost aimed at us, is what that.
Yeah, exactly. Well, it's very close.
Very close.
Yeah, and the thing is, these things are extended because of the way they process the data.
Right.
You're not going to get beautiful circular-looking shadows of black holes like you have an Event Horizon Telescope.
Right.
But the separate sources you're seeing here are real. So you get the separation, interferometry of the fringe patterns and stuff.
Right.
That there's structure here. That
Because
you can
that's what
see.
you really get with an interferometer.
Now, you can do modeling of these observations, and that's the next slide that we have. So what we think is going on is you have the main black hole, the more massive of the two, that you see in the bottom of this illustration. It has an accretion disk, and there is a jet. The primary jet sort of goes in the upper left. And then in orbit around the primary black hole is the lower mass black hole, the secondary. And the illustration, which can be confusing a bit, is showing you the secondary one at two different locations. It's not like there's three black holes in the system. And it orbits in sort of a clockwise fashion as viewed, for this model, the way it's set up, this drawing. And it also has its own jet. So there's a fainter jet due to the second black hole. And the location of us is those three black arrows you see sort of pointing almost straight up, but not quite, off to the left a little bit. That is in the direction of the Earth. So that's our eyeball looking down at this system. And this is the best interpretation we have of those images, those really high resolutions images that we have obtained.
What you're telling me. We need more data.
Yeah, so really what it means is the instrumentation is getting unreal. Like it's really, really advancing. And so there's only great hope for the future. Now, if you're interested in this kind of stuff, if you want to learn about black holes and what makes them tick, if you want to learn about what it requires to build the next generation of instrumentation that allows to see at even higher resolutions, come to places like the University of North Dakota.
Yeah.
We have lots of programs here that you could take both on campus and online. It's up to you. But we have a wide range of, hopefully, of interest to almost everybody that's out there. And you don't have to be 20 years old to take this stuff. You can come as if you're like a lifelong learner. Even if you're 50 years old, you can certainly get online and do these sort of programs at your own sort of pace.
At your own pace. Or show up here, come talk to Wayne and I, and we'll show you around. So.
Exactly. Now, our next podcast will be on October the 21st. And at this 5 p.m. Central Daylight Time still.
Daylight
is
time
soon
still.
getting point. We're going to change that.
Yep.
And it's getting close. And you can tell because the days are a lot shorter. In fact, it's getting a lot cooler now. So everybody's kind of predicting when are we going to see that first snowflake. We should have a contest.
Yeah,
you can
start a pool.
Yeah, so everybody see who's right. You got to say the day and the hour.
Okay.
And then whoever gets closest wins. You see, that's how that would work. But we always leave you with a quote at the end of our podcast. So today I decided to have a quote from a very famous physicist who's no longer with us, Richard Feynman.
Feynman, okay.
And here's his quote. Students don't need a perfect teacher. Okay. Students need a happy teacher who's going to make them excited to come to school and grow a love for learning.
Like that one.
If you like our podcast, please don't forget to give us a thumbs up, smash that like button, subscribe if you haven't subscribed.
Yep.
And thank you very much for watching.
See you later, folks.